Alright, hello everyone. Today we are going through 9.6 and 9.7 of the AP Chemistry curriculum. First, we're going to talk about free energy of dissolution. Dissolution depends on the balance of enthalpy and entropy, which together determine free energy, or delta G. When a substance dissolves, energy is used to break forces in the solid, and energy is released when new interactions form with the solvent. At the same time, the arrangement of particles becomes more or less ordered, affecting entropy. Although we can estimate each of these contributions, predicting whether dissolution will be favorable is difficult because these energy changes often cancel each other out. To dissolve a salt, the strong electrostatic forces holding the ions together must be overcome. This requires energy, making this first step in dissolution endothermic. The stronger the ionic lattice, the more energy that is needed to break it apart. Water molecules are strongly hydrogen bonded to each other. In order to make space for those ions, some of those interactions must be disrupted, which also requires energy and therefore is endothermic. The third step of dissolution is when the ions are surrounded by water molecules. The negative and positive ends of the polar water molecules orient around the ions, forming really strong ion-dipole interactions. This releases energy, so this is the only step of dissolution that is exothermic. The overall enthalpy change of dissolution is the sum of these three effects. Whether it's positive or negative depends on which step is dominating. When a crystalline solid dissolves into free ions, the system becomes more disordered. That transition from a highly ordered solid to dispersed ions in solution usually results in an increase in entropy or a positive delta S. A positive delta S helps drive the dissolution process forward because it contributes a negative term from the equation. So by increasing delta S, we are adding a more negative component to solving for delta G. So by increasing the entropy, we're also going to decrease delta G. Whether dissolution actually happens can be predicted based off of the Gibbs free energy change in the equation here. This factors in change in enthalpy, temperature, and entropy. If delta G comes out as negative, then we know that the dissolution is thermodynamically favored, meaning that substance is soluble. If delta G comes out to be positive, then dissolution is not favored, and the substance is insoluble or only slightly soluble. Whether delta G is negative depends on the balance between enthalpy, entropy, and temperature. So sometimes you'll have a positive delta H, which is endothermic, and we know an endothermic reaction is not typically favored, but it can be overcome by a very large positive change in entropy, which can promote that favorability, making the overall delta G negative. Even though we can estimate delta H and delta S with dissolution, predicting solubility is often quite difficult because of those three steps that we talked about earlier in the video. So those endothermic and exothermic steps can sometimes cancel each other out, which makes it really hard to predict delta H for dissolution. Entropy, however, usually increases during dissolution because we're going from an ordered solid to aqueous ions, which does help favor the process, but its effect depends on temperature and how much disorder increases overall. All right, the table above lists the equilibrium constants and changes in thermodynamic properties for the dissolution of FeCO3 and MnCO3 at 25 degrees Celsius. The two particle diagrams below represent saturated solutions of each compound at equilibrium. So looking at the table, I can see my delta H and my delta S values are the same, both reactions give a negative delta H and both reactions give a positive delta S. Then looking at my KSP, I can see that iron 2 carbonate has a larger KSP value, meaning it's going to create a larger amount of products than MnCO3 would. The question says, which of the following explains the properties listed in the table is best represented by the particle diagram? So with these types of questions, it's really important to listen to the end of the question where it says best represented by the particle diagram. So a lot of these types of answer choices are going to be correct statements, but we're specifically looking at what is represented by the particle diagram, which is down on the bottom here. Now, as we talked about in previous slides, delta H is really hard to completely estimate because we know that there's those 3 steps happening: the ionic compound being broken apart, the water molecules being separated from their hydrogen bonds, and then finally the solvation process. That is not shown by the particle diagram, right? So that automatically cancels out A and B because the particle diagram does not show how we get a negative delta H. Then going to C, it says delta S is greater than 0 because both compounds produce a very small amount of ions. Well, delta S doesn't depend on the amount of ions, it's just showcasing disorder. So both of these are showcasing disorder because we are going from a solid ionic compound into dissolved ions. So that's not a very good statement. Then D says the molar solubility is greater for FeCO3 compared to MnCO3. Now, this would be a great option if the particle diagram represents that. So let's double check that it does. So looking at the key, I'm going to check carbonate. So for FeCO3, I make 1, 2, 3, 4, 5, 6 carbonates. And then for MnCO3, I make 1, 2, 3, 4, 5 carbonates. So this particle diagram is clearly representing that the molar solubility of FeCO3 is greater than MnCO3. So D would be your correct answer. At 298 Kelvin, which remember is room temperature, ammonium nitrate readily dissolves in water, suggesting that the change in free energy favors the dissolution process. So if this is saying favors the dissolution process, that means we know we have a negative delta G. However, when ammonium nitrate dissolves in water, the temperature of the water decreases. So if the surroundings is decreasing in temperature, we know we have an endothermic reaction or positive delta H. The particulate diagram above attempts to provide a microscopic view of the dissolution of ammonium nitrate, considering both the change in enthalpy and the change in entropy. Which of the following explains what the particle diagram is able to illustrate and why? So before we answer the question, I want to go over a few things. Number 1, we know that we have a negative delta G, but we also know that we have an unfavorable process with enthalpy, which is an endothermic reaction. So if our delta G is negative and our delta H is positive, I know my delta S, has to be very high in order to overcome that endothermic process. So what I'm really looking for in my particulate diagram is it showcasing that positive change in entropy? And we can see that it does because it's illustrating that the ammonium nitrate ions are ordered in a crystal lattice at the beginning and then become separated and dispersed throughout the water after dissolving. So that means that the particles are more spread out and the system is more disordered, meaning a positive delta S. So the answer to this question would be that the particle diagram is able to illustrate that entropy increases when ammonium nitrate dissolves in water because the ions disperse in solution. Two students prepared aqueous solutions of lithium chloride and measured the properties as in the table above. Both students observed that the solid lithium chloride readily dissolved in water. The students drew particle diagrams to explain the changes in the enthalpy and entropy of dissolution for lithium chloride. Based on this information, the better particle diagram was drawn by which student, and why is that diagram more accurate? So first, looking at these two diagrams, you can see that student 2 does not separate lithium chloride into its constituent ions. They are still together, which is highly inaccurate for dissolving a soluble ionic compound. So right away, we can tell that student 2 does not have a correct particle diagram. Now, student 1 does in fact separate lithium and chloride ions, and they are correctly positioned near the correct parts of the water molecule, meaning I know if I have a water molecule, oxygen is much more electronegative, which means this is going to be the partial negative end, whereas our hydrogens are going to be partial positive end. So our chlorine ions are going to be attracted to the positive end of the water molecule, which is the hydrogens, and our lithium ions are going to be attracted to the negative end of the water molecules, which is oxygen, and that is clearly represented in this particle diagram. What's also represented is the change in entropy. So we know when we are dissolving an ionic solid, we are increasing entropy because now we have more disorder. So those ions that make up the ionic solid are now separated and more dispersed, which is then more chaotic and therefore an increase in entropy. So the answer to this question is the better particle diagram was drawn by student 1 because the lithium chloride dissolves in water and it dissociates into Li plus and Cl minus ions, causing an increase in entropy. All right, and for our last practice for 9.6, it says high solubility of an ionic solid in water is favored by which of the following conditions? So we're looking for conditions that increase solubility. Number 1 says the existence of strong ionic attractions in the crystal lattice. So we know if we have really strong attractions in our solid, it's going to take a lot more energy to break it apart, which is an endothermic reaction. And if that endothermic reaction is too great, then we're not going to have a super soluble salt. So this would not be one of our answer choices. Number 2 says the formation of strong ion dipole interactions. That is true because once our salt is dissolved, if there is a strong connection between, let's say, a chloride ion and the hydrogen in water, if that interaction is really strong, then that's going to give us a lot of stability once those ions are dissolved in water. So yes, that would help increase solubility. And then 3 says an increase in entropy upon dissolving. So we know our delta G equation is delta H minus T delta S. If we have a very large change in entropy or a very large delta S, that's increasing this part of the equation, which is making delta G more negative. And we know if we have a negative delta G, we are increasing solubility of our salt. So this would also be a correct answer. All right, now moving on to 9.7, which is on coupled reactions. Thermodynamically unfavorable reactions can occur by using external energy like electricity or light, or by coupling them to favorable reactions. In coupled reactions, the processes share intermediates, and the overall reaction has a negative delta G, making it spontaneous. So thermodynamically unfavorable reactions, which is denoted by a positive delta G, don't occur spontaneously by definition. However, we can encourage them to occur in 2 separate ways. The first one is by using an external energy source like electricity or light. And the other option is by coupling them with an already favorable reaction. And then the overall process, we just have to make sure it's a negative delta G, and therefore it has become thermodynamically favorable. Non-spontaneous reactions which have a positive delta G don't occur on their own, but they can be driven forward by adding energy from outside the system. This added energy helps overcome the unfavorable thermodynamics and pushes the reaction to proceed. A very common example of this is electrolysis, where electrical energy is used to force redox reactions that would not normally occur. So in this process, electrons are driven through an external circuit, causing the oxidation at the anode and the reduction at the cathode, allowing the overall reaction to take place despite being non-spontaneous. So here in this diagram, we have a solution of ions. So let's just, for simplicity, say that this is sodium chloride. So we have liquid or molten sodium chloride in solution. So we have a bunch of Na plus ions, and then we have a bunch of Cl minus ions. Now, if we were just to let that molten or liquid sodium chloride sit, nothing would happen. It would not dissociate into its components, solid, sodium, and chlorine gas. However, if we were to add an external energy source like this battery, then we can in fact create solid sodium and chlorine gas. And I'm just going to quickly show you how this works. We do have an entire lesson on it. But essentially what happens is we add in this battery here. This is going to create an energy change. And we have this positively charged anode, and we have this negatively charged cathode. Now, obviously, our anions, or our negatively charged ions, in this case chlorine, are going to be attracted to the positive energy source. And when that chlorine comes in contact with this anode, it's actually going to oxidize and release its electron. And this electron is going to travel along this circuit until it reaches the cathode. And when it reaches the cathode, this electron that came from the chlorine is now going to attach to this sodium plus ion and create solid sodium. And that solid sodium is then going to plate onto this cathode, and this cathode is going to gain mass of the sodium solid. But the key thing from this slide is that that reaction would not occur without that added battery. So the battery is driving this reaction. Another way that we can drive an unfavorable reaction is with light, and a very common example of that is photosynthesis. So even though photosynthesis has an overall positive delta G, plants absorb energy from the sunlight to power the reaction, and that's going to allow carbon dioxide and water to be converted into glucose and oxygen. Another way to drive a non-spontaneous reaction is by coupling it with a highly favorable one. If the two reactions share a common intermediate, their combined effect can result in an overall negative delta G, making that process spontaneous. This is very common in biological systems. For example, cells often couple unfavorable reactions to ATP hydrolysis, which releases a large amount of energy. In the diagram, you can see the direct formation of sucrose from glucose, and fructose is not favorable. But when it's coupled to ATP breaking down, the overall reaction becomes favorable and therefore can proceed. For coupled or multi-step reactions, keep in mind that the overall Gibbs free energy change is simply the sum of the delta G values for each individual step. So this means that even if one step is non-spontaneous, it can still occur if it's paired with a more favorable step. As long as the total delta G is negative, the entire process is thermodynamically favorable and can happen spontaneously. So looking at this particle diagram, we can see that in this electrolysis example, the switch is open, which means there is no energy source right now. And with that, our molten NaCl is just how you would expect. We have our Na plus ions and we have our Cl minus ions. Now when we close the switch and we have this process forming, remember we talked about the chlorine ions are going to be attracted to the positive anode, and these electrons are going to travel over to the cathode, and they're going to react with our Na plus ions, and that is going to create solid sodium that will be on the cathode. So we just talked about this. This is showcasing that without the electricity, which is here, nothing is happening. However, when we add electricity, then we actually have a reaction. So this is showcasing that without the energy, it is a non-spontaneous reaction. However, when we add in the energy source, then it becomes a thermodynamically favored reaction. All right, and then our last example for this video, the equations shown in the table below represent two chemical reactions. A student proposes coupling the two reactions to produce Cu through a thermodynamically favorable process. Which of the following reaction systems best support the student's proposal? So first, let's look at these two reactions. They want to form copper from copper 1 sulfide. However, that reaction has a positive delta G, meaning it is not thermodynamically favorable. However, one of the products in reaction 1 is sulfur. And in another reaction that is very favorable, uses sulfur and oxygen gas to form sulfur dioxide. So because they have an intermediate, we can actually combine these two reactions and get an overall negative delta G. So first, let's get our net reaction, and that is going to be canceling out our sulfur. So we're going to have Cu2S plus our other reactant, O2. And then we're going to combine our products, 2 Cu and 1 SO2. So that's our net equation. So this one would not be correct. This one would not be correct. And this one would not be correct. So we're automatically, this is our answer, but we're just going to go over delta G as well so you know how to solve it. If you need to get an overall delta G for a coupled reaction, remember you're just going to add the delta G values. So it's going to be positive 90 plus negative 300, which would give us negative 210.